So we have figure 9 shows the graph of x, ln of x squared plus 2, and the tangent is drawn at x equals 1. Okay, part A, show that the derivative function is this. So, with a conjecture problem, it'll start easy and will get harder. You have to make sure you get the easy marks. So this is A part 1. Now, our original function is x ln of x squared plus 2. So when I'm looking at this, we need to use the product rule because we have u times v. Now when we differentiate an ln function, ln of f of x goes to f dash of x on top of f of x. And I might put it up here just to save a little bit of space. dy on dx is u dash v plus u v dash. Now, whenever a question tells you show that, okay, show that, you really need to show everything involved. The marker's not going to make assumptions on your behalf. You need to demonstrate that it's true. So that's why I've gone, yep, u times v plus u dash v plus u v dash. I'm really showing it nice and clearly. Okay, that's A part 1. Part 2, hence show that the tangent to the graph at x equals 1 has this equation. So we're finding a tangent when x is 1. This is going to be A part 2. So for a tangent, we need two things. We need the point of contact. Okay, x is, let's do it a little bit different. Let's use the formula today. For the formula, f dash of a, x take a, plus f of a. All right. So, and we're doing at a is, x is 1. That's where we're finding the tangent for the first one, isn't it? At x is 1. Good. Okay, so that means we're finding f dash of 1 times x take 1 plus f of 1. All right, so you might find you really prefer this process because we don't need to solve it through for C. If you do prefer the formula, you're very welcome to do it. Okay, so f dash of 1. This is my derivative function. So if I put the number 1 into the derivative function, that's going to be my f dash of 1. So it's going to be ln of 1 plus 2. That's going to be ln of 3. Plus, and then over here we'll have 2 on top of 3. Okay, that's the whole f dash of 1 part, multiplied by x take 1. Okay, that stays as is. And then f of 1, well, that's the y value. When x is 1, I put 1 into the original function. 1 ln 3. Alright, so just where we get that from, f dash of 1, I put the number 1 into the derivative function, that goes there, x take 1 plus, I put 1 into the original function, that goes there. Now, we have a little bit to do here, a bit of expansion. So, ln 3 plus 2 on 3, x take 2 on 3. Alright. Let's, what we're going to do is we're going to distribute this. Alright, so we've got ln 3 plus 2 on 3 times x. So I'm multiplying that term by x. And now I'm going to multiply it by minus 1. Okay, so all I've done is I've multiplied that. I'm treating this as one term. I've got that times x and that times minus 1. Okay, that times x, that times minus 1. I've got minus ln 3, take 2 on 3. And then we can see minus ln 3 plus ln 3. That will cancel, and we're left with what it told us to find. mx plus c. Okay, here's the slope, Tyler. Here's the y-intercept. Okay, get a mark for part 3. Look at that. Determine the y-intercept of this tangent. Well, mx plus c, this is the y-intercept, the yint. All right, so we've got to make sure we get those marks. Now, consider the family of functions of the form x times ln x to the n plus n. The table below shows the y-intercept to the tangent for the graphs at x equals 1. So we're always doing the tangent at x is 1. And so if we have, let's make up, I'll draw it here, x ln x to the 3 plus 3, x ln x to the 4 plus 4, x ln x to the 5 plus 5. And it's going to say make a conjecture about x ln x to the n plus n. And we're given the y-intercepts. Here we've got minus 3 on 4, minus 4 on 5, minus 5 on 6. We saw in the first circumstance it was minus 2 on 3. So here we have n is 3, n is 4, n is 5. Here we have n. Can we see a relationship? So, look at the top. That number's the same. 4 and 4, 5 and 5. So that means for n, at the top we're going to have n. We've got this negative out the front. And what's going out the bottom? N plus 1. Very good. It's 1 larger than n. Excellent. All right, so I do want to rub that out so I can prove the conjecture. I want to use all that board space. But is everyone okay with how we've arrived at that number? That number's there, and then we've got 1 larger. It's always 1 larger than the top number. So if this is our function, that's what we'll have. Okay, so it wants us to prove the y-intercept of the tangent at x is 1, and the function we're talking about is x ln x to the n plus n. Okay, that's the function. So all we need to do is find the tangent to this function at x is 1. Easy. All right, find the tangent at x is 1. So let's, again, we were using the formula before, let's just keep doing that. So for the formula, we're going to have f dash of 1 times x take 1 plus f of 1. All right, here's f of x. So we are going to need to differentiate it again because it's a different function this time. Before we had x squared, now we have x to the power of n. So u is x and v is this part here, ln of x to the n. U dash will be 1, and V dash will be, this is probably the tricky step here, finding the derivative of ln x to the n. But it's just the power rule. The derivative of x to the n is n, x, n take 1. That's what goes at the top. So when we have ln of a function, f dash of x at the top, f of x at the bottom. So u dash, v, we've got ln of f of x, f dash of x on top of f of x, that's staying the same, And then the derivative of x to the n is this, and n is just a number, so that part's gone. That's how I'm justifying that. Okay, don't be alarmed. All right, so smash that together for the derivative. U dash v plus u v dash. Now, we can simplify it, right? We can collect these, x times x to the n take 1. They're the same base, but we don't need to, okay? Because we want the slope when x is 1, all right? F dash of 1, that's going to go there for our formula. So let's just evaluate that here, right below f dash of x. F dash of 1 is going to be ln of 1 plus n. Because 1 to the power of any number is just 1. And then over here we'll have 1 times n times 1 on top of 1 plus n. And we can simplify that just a little bit. So we've got that f dash of 1, that's going to go there. And f of 1 we can get straight from here. F of 1 is just going to be ln of 1 plus n. All right, let's smash it all together. So the equation of the tangent is ln of 1 plus n on 1 plus n. Okay, f dash of 1 multiplied by x take 1, okay, plus f of 1. So that's when I put 1 into the original function, and that's just going to be ln of 1 plus n. All right, we're so close. Let's expand this out. So I'm going to multiply this term by x, okay, that whole thing by x. That's going to give me ln of 1 plus n on 1 plus n x, okay. So I've multiplied that by x, and now I'm going to multiply it by minus 1. So it makes that negative, and that negative, plus ln of 1 plus n. Okay, minus ln of 1 plus n, plus ln of 1 plus n. They're going to cancel, and we're left with minus n on 1 plus n. This is the equation of the tangent at x equals 1 to this function. Y equals mx plus c. This is the y-intercept. What was our conjecture? Minus n on 1 plus n. So we can just finish which has y-int, which has a int, minus n on 1 plus n, Q, E, D. All right, so when I'm going through a really long problem like this, okay, if you find there's somewhere you get lost, just make a scribble on your page and say, explain that part to me. What did you do there? Because we're bringing a lot of things together here, but notice it's just the same skills. Yeah, it's increasing, like, I mean, that's an enormous complex mess, but we just treat it carefully. This is some number. We just treat it as if it's a number. It's a number times x, a number times minus 1. And so that's what I'm doing. There's the number times x, multiplied it by minus 1, cancelling like terms. Okay, so the same skills apply. Any questions about that one? Really good. So as far as tangents go, there's a couple more questions you can do in the book. So in the email, what did I say in the email? I'll bring that up. Oh, by the way, question 8 in the textbook is a conjecture question. That's not too bad a one. You can have a go at that. And the other conjecture problems, so we've done 2 and 3. You can do question 5, you can do question 11, and you can do question 12. So, not that you have to do them for homework this weekend, they're tough. And we've also got worked solutions in the OneDrive that you can use to support it. Alright, so we've still got about 7 minutes, guys. Might be enough to do the next question. You know, if we packed up 7 minutes early every lesson, that's 20 minutes a week, 200 minutes a term, that's 3 double lessons a term.
Still got.
Oh, thanks, mate.